farming the BASEL problem with a little Fourier Series Fun. In 1807, Joseph Fourier stated the following theorem. Any single-valued function f of x, defined on the interval from negative pi to pi, may be represented by the following trigonometric series. A sub 0 over 2 plus the infinite series starting from n equals 1 of a sub n cosine nx plus b sub n sine nx. The coefficients of the series, a sub n and b sub n, are given by Euler's formulas. A sub n is equal to 1 over pi, the integral from negative pi to pi, of f of x cosine nx dx, and ranging starting from 0, 1, 2, and so on. B sub n is 1 over pi, the integral from negative pi to pi, of f of x sine nx dx, where n runs starting from 1, 2, 3, and so on. The BASEL problem. The infinite series starting from n equals 1 to infinity of 1 over n squared. The value of this is equal to pi squared over 6, discovered by Leonhard Euler. Now, in order for us to calculate this value, we're first going to find the Fourier series expansion of f of x is equal to x squared on the interval from negative pi to pi. Graphing this function on the interval from negative pi to pi, we can see what it looks like outside of this interval. Its periodic representation graphed here. F of x equals x squared is going to be given by the Fourier series formula, a sub 0 over 2 plus the infinite series starting from 1 of an cosine nx plus bn sine nx. So first we begin by calculating a sub 0. This is the integral of 1 over pi from negative pi to pi of x squared dx. A simple integral to evaluate, and a sub 0 works out to be 2 pi squared over 3. So the first part of our series, a sub 0 over 2, would be equal to pi squared over 3. The next part of our strategy will be to calculate the coefficient a sub n. Using Euler's formula, 1 over pi, the integral from negative pi to pi, of x squared cosine nx dx, we're going to exploit the fact that x squared cosine nx is an even function, and this being integrated over a symmetric interval. So therefore we can write this as 2 times the integral from 0 to pi. Now this integral we're going to find by doing integration by parts. So the integral of x squared cosine nx dx, we're going to set it up by first making a clever substitution. We're going to let y equal nx, and therefore 1 over n dy is equal to dx. This is going to allow us to write x squared as y squared over n squared, and our integral then becomes I equal to the integral of y squared over n squared, cosine of y, 1 over n dy. We can pull some of the constants out front there, so a sub n would be 2 over pi n cubed, the integral of y squared cosine y dy. Now we can handle this with integration by parts a little easier. letting u equal y squared, and that gives us du equals 2y dy. dv will be cosine y dy, so v is equal to sine. We begin by writing out the integration by parts formula, and because of the fact that with sine and cosine, we'll have to do this one more time to get to our result. So applying integration by parts a second time on that integral that remains there, letting u equal 2y and dv equals sine of y dy. We can put this all together from integration by parts and get y squared sine of y minus the quantity negative 2y cosine y plus the integral of 2 cosine y dy. That last integral evaluates to 2 sine y. And the limits of integration here are going to be from 0 to n pi. Those limits changed when we made the substitution of y equals nx. So now a sub n is equal to 2 over pi n cubed times 2 pi n cosine n pi. And cosine n pi is the same thing as negative 1 to the nth power. So a sub n ultimately evaluates to, and let's put it together with the function f of x. F of x is equal to x squared is going to equal to, we first found pi squared over 3 plus the infinite series, and the coefficient for a sub n is negative 1 to the nth power times 4 over n squared. So the last thing that we need to calculate here before finding the infinite series is this coefficient b sub n. And here we're going to exploit the fact that the integrand is an odd function over a symmetric interval, and that's going to evaluate to 0. So that part drops out of the formula. So now putting this all together, f of x is equal to x squared, which is going to be represented by the trigonometric series pi squared over 3 plus the infinite series n starting at 1 to infinity of negative 1 to the nth power 4 over n squared cosine nx. And this is our Fourier series expansion of x squared over the interval negative pi to pi. Now it is from this point that we're going to use this Fourier series expansion to evaluate the BASEL problem, the infinite series of 1 over n squared. Now since x is an element in the interval from negative pi to pi, we're going to let x equal pi. So f of pi, evaluating this function at pi, will give us pi squared on one side of the equation, and then on the other side we have pi squared over 3 plus the infinite series where we plug in x equals pi. That'll give us a cosine of n pi, which, like before, is the same thing as negative 1 to the nth power. So we get an infinite series that, when we factor a few things out, we're getting the infinite series of 1 over n squared, which is the value that we're trying to get to for the BASEL problem. And lo and behold, we get pi squared over 6, the value of the infinite series starting at 1 to infinity of 1 over n squared. Now, if you're not familiar with the BASEL problem, this is also related to something called the Riemann zeta function. Zeta of z is equal to the infinite series from 1 to infinity of 1 over n to the z power, where z can be a complex number. Evaluating the zeta function at 2 is the BASEL problem that we just found, and its value is pi squared over 6, found by Leonhard Euler. This is what we would consider an exact value in terms of pi. The exact values for all the even inputs of the zeta function are actually known and can be computed in a similar fashion. As an open problem, however, it's all the odd inputs of the zeta function that, although they converge to values, we do not know if they have exact value representations. Zeta 3 is irrational, but it is not known if it is transcendental. Maybe you can figure it out. I hope you enjoyed this video. Thanks for watching. please hit that like, subscribe, and notification bell for more videos. Stay tuned.